We finished this lecture with consideration of anisotropic but spatially homogeneous solution, cosmological-like solutions. And that will help us to understand better the homogeneous and isotropic solutions. So these are so-called Kasner solutions. So the Kasner solution corresponds to the following metric: dt squared minus x squared of t times dx squared minus y squared of t times dy squared minus z squared of t dz squared. So this is exactly, well, first of all, it's spatially homogeneous because these are functions independent of spatial coordinates, so they're functions of time only. But it's anisotropic because every direction scales with different scale. Only when these are equal to each other, we reduce to the previous case of k equal to 0. I mean, when the spatial sections are flat. So we are going to discuss the vacuum solution. So when energy momentum tensor is 0. Energy momentum tensor is 0. So for this case, one can calculate Ricci tensor. The non-trivial components of the Ricci tensor are as follows. It's theta dot. What is theta I will explain in a moment. The notations I will explain in a moment. A squared plus b squared plus c squared. And R11 is equal to minus a dot minus theta a. R22 is equal to minus b dot minus theta b. R33 is equal to minus c dot minus theta c. And who are A and B and C? A is equal to x dot over x. Dot means differential with respect to time, here and here. So A is just this x dot over x. B is y dot over y. And C is z dot over z. This is z. And theta, standing here, is actually A plus B plus C. So these are the expressions for the non-trivial components of Ricci tensor for this metric. Now, the energy momentum conservation condition for this case is R dot plus theta times P plus rho equals to 0, in case if P and rho are both non-zero. So because we consider the case of t mu equal to 0, so both rho and t equal to 0, both rho and p equal to 0, then, so this equation we don't need, but just for general discussion we listed it here. So the condition, the 0, component of Einstein equation imposes this condition, that minus AB minus BC minus CA is equal to 0. This is 0, component of Einstein equation. As a result, because this is 0, from this, one sees that theta squared is just A squared plus B squared plus C squared. Hence, again, using this, one vacuum Einstein equation is R00 equal to 0. This is not the same. This is R00 minus 1/2 G00R equal to 0. So, but from R00 equal to 0, vacuum Einstein equation, we obtain from here that theta dot plus theta squared equal to 0. The solution of this equation obviously is theta equal to 1 over t minus t0. And adjusting time by time shift, we can put this to 0. So now one can use this equation to find that minus a dot is minus a theta is equal to 0. But from the fact that theta is equal 1 over t, from here we can obtain that a is equal p of t for so far any p. P can be any. Similarly, from this equation and from this equation, we obtain that b is equal to q over t and c is equal r over t, where p, q, and r so far arbitrary constants of integration following from the equations similar to this one. We are discussing Kasner-like solution, which is anisotropic but spatially homogeneous, and we have introduced the notation that theta, that there is a theta, which is x dot over x plus y dot over y plus z dot over z. And at the same time, we have obtained the condition that theta squared is actually, from the Einstein equation, it follows that we had the notation that this is A, this is B, this is C. And from the Einstein equation, we have obtained that this is A squared plus B squared plus C squared. That's what we have obtained. And also from the Einstein equation, we have obtained that this is 1 over t, and x dot over x is equal to p over t, y dot over y is equal to q over t, and z dot over z is equal to r over t, where so far p, q, and r are constants of integration, arbitrary constants of integration. But from here and this relations, we obtain that p plus q plus r is equal to 1, and p squared plus q squared plus r squared is equal to 1. This is the conditions to which p, q, and r are subject to. Now, one can solve this equation for x, for y, and for z, and plug them there. After the proper rescaling of this coordinate, this coordinate, this coordinate, one can get rid of the constants of integrations which appear here. And to obtain that, the Kasner metric is as follows, that ds squared is dt squared minus t to the power 2p dx squared minus t to the power 2q dy squared minus t to the power 2r dz squared. So you see Kasner's solution describes the following situation. As the time goes by, we have that these three directions are independently, not related to each other, expanding with different, or shrinking depending on where time goes. Independent, that they are in different manner expand with different powers. So let us explain why one physical situation where the Kasner solution appears, naturally appears. Consider Schwarzschild metric under the horizon. So it means that we consider the following metric, dr squared 1 minus, rg over r minus 1 minus rg over r 1 minus 1 dt squared minus r squared d omega squared. And here r is less than rg. So this is this is not a Schwarzschild metric, not quite that, but it does solve Einstein equations for this value of R. And these R and T are not directly related to R and T in Schwarzschild solution, but they are related to the Kruskal coordinates, and that's how they can be related to the coordinates, Schwarzschild, standard Schwarzschild coordinates. Anyway, this solution describes space-time under the horizon for these values, and it is not time independent because R is now playing the role of time and T is playing the role of spatial coordinate. So now let us consider the situation that R is going to 0. In this limit, one can neglect this and obtains the following metric that ds squared becomes approximately R over Rg dr squared minus Rg over R dt squared minus R squared d omega squared. Remember that here we have angles, d theta squared, etc. Now let us make the following coordinate change. Let us change R over Rg square root dr, denoted as dt. Then 2Rg over 3 1/3 dt we will denote as dx. Then 3 over 2 square root of Rg to the power 2/3 d theta, which is here, we denote as dy. And finally 3 over 2 square root of Rg divided to the power 2/3 d phi is actually we denote as dz. After these changes, this metric acquires the following approximate form for small values of angles. Let me first write the metric and explain the approximation. It's t to the power minus t to 3 dx squared minus t to the power 4/3 dy squared minus t to the power 4/3 dz squared. And here t goes to 0. T goes to 0. As t goes to 0, the angles theta and phi, the big difference between two values of theta and two values of phi, are causally separated from each other. Are not, as t very small, the points which are big distance away from each other by big angles are causally separated. That's the reason we can consider physically meaningful situation that theta is here. We assume that theta is of order of 0, very close to 0, and phi is very close to 0. So we don't consider big differences in theta and phi because they are causally separated. And now one can see that this metric is exactly of this type. Exactly of this type, with the only difference that t is going to 0. And we have concrete values of P, Q, and R as follows from here. And they do indeed obey this condition. So in fact, as we are approaching the singularity of the Schwarzschild metric, we encounter cosmological, like in homogeneous but anisotropic, Kasner-like solution, which is vacuum-like. In fact, which is vacuum solution, because in fact, a Schwarzschild solution is a vacuum solution, and this is a vacuum Kasner solution. This is a condition for P, Q, and R for the vacuum solutions. And it's important that, in fact, it's a generic phenomenon that as we approach some singularities in space-time, we encounter in the vicinity of the singularities this kind of behavior for the metric, for the different values of x, y, and z. But it's not necessary have to be vacuum Kasner solution, just because it depends on the energy momentum tensor. In case if energy momentum tensor is not zero, one encounters this solution in the vicinity of the singularity, but non-vacuum type. So that's the end of the story for the standard cosmological solutions. And next lecture we will discuss cosmological solutions with non-zero, cosmological type solutions with non-zero cosmological constant.